What if everything you know about space travel is already obsolete? For more than half a century, humanity has relied on chemical rockets. The same basic technology that powered the Apollo missions continues to launch satellites today. While these rockets are powerful enough to escape Earth's gravity and explore our solar system, they are fundamentally incapable of taking us to another star within a human lifetime. The nearest star system, Alpha Centauri, lies 4.37 light-years away. At the speed of today's fastest spacecraft, reaching it would take tens of thousands of years. Entire civilizations could rise and fall before a single probe arrived. Yet a revolutionary propulsion system known as the direct fusion drive may finally change that reality. Instead of relying on chemical combustion, this concept harnesses the same power source that fuels the sun itself: nuclear fusion. And as of 2026, fusion-powered interstellar travel is no longer confined to science fiction novels. Engineers and physicists are actively developing technologies that could make journeys to the stars achievable within a single generation. To understand why fusion changes everything, we need to understand the limitations of conventional rockets. Chemical propulsion works by burning fuel and oxidizer to create hot gases that are expelled through a nozzle, generating thrust. It is effective for launching from Earth, but the energy density of chemical fuel is extremely limited when compared to nuclear processes. Fusion reactions release millions of times more energy per kilogram than chemical combustion. This means a spacecraft powered by fusion could accelerate continuously for months or even years, gradually reaching speeds that chemical rockets could never achieve. Instead of traveling at a tiny fraction of 1% of light speed, advanced fusion-powered vessels could theoretically reach around 5% of light speed. That may not sound impressive at first, but at those velocities, the impossible suddenly becomes possible. A journey to Alpha Centauri that once required tens of thousands of years could potentially be completed within decades, placing interstellar exploration within reach of people alive today. At the heart of this concept is the direct fusion drive, often described as a magnetic fusion torch. Imagine a spacecraft carrying a compact fusion reactor surrounded by powerful superconducting magnets. Inside the reactor, plasma is heated to temperatures hotter than the core of the sun. Under these extreme conditions, atomic nuclei fuse together, releasing enormous amounts of energy. Instead of using that energy solely to generate electricity, magnetic fields channel the superheated plasma directly out the back of the spacecraft, creating thrust. The result is an engine unlike anything humanity has ever built. Unlike chemical rockets that burn fuel rapidly and provide short bursts of acceleration, a fusion engine could operate continuously day after day, year after year. The spacecraft would slowly but relentlessly accelerate across the vast emptiness of interstellar space until it reached velocities once considered impossible. But speed alone is not enough to reach another star. One of the greatest mysteries of interstellar travel is survival. Deep space is an incredibly hostile environment. Outside Earth's protective magnetic field, astronauts are constantly exposed to cosmic radiation, energetic particles from distant supernovae, and powerful bursts of radiation from stars. Over the course of a decades-long mission, this radiation could become lethal to both humans and spacecraft systems. Then there is another threat that few people think about: interstellar dust. At 5% of the speed of light, even microscopic particles become deadly projectiles. A tiny grain of dust striking a spacecraft at such velocities can release tremendous amounts of energy. To overcome these dangers, engineers are exploring advanced shielding concepts, including magnetic fields capable of deflecting charged particles, hydrogen-rich protective layers, plasma shields, and even artificial magnetospheres surrounding the spacecraft. These technologies may sound futuristic, but they are based on real physics and active areas of research. Another enormous challenge is deceleration. Most discussions about interstellar travel focus on reaching incredible speeds, but very few people ask the obvious question: how do you stop? A spacecraft traveling at millions of kilometers per hour cannot simply slam on the brakes when it reaches its destination. Without a deceleration system, it would fly past Alpha Centauri in a matter of days. This is one of the reasons fusion propulsion is so important. The same engine that accelerates the spacecraft can also be used to slow it down. Some proposed designs would reverse the direction of thrust halfway through the journey, gradually reducing velocity as the spacecraft approaches its target. Other concepts involve enormous magnetic sails that interact with stellar winds and interstellar particles to create braking forces. Solving the deceleration problem transforms an interstellar flyby into a true exploration mission capable of studying planets, moons, and potentially habitable worlds up close. And Alpha Centauri itself is an incredibly compelling destination. It is not just a single star, but a complex system consisting of 3 stars bound together by gravity. Most intriguing of all is Proxima Centauri, a red dwarf star that hosts at least one known planet within its habitable zone. This planet, known as Proxima Centauri b, orbits at a distance where liquid water could potentially exist. Scientists still do not know whether it possesses an atmosphere, oceans, or conditions suitable for life. The only way to answer these questions definitively is to send spacecraft capable of examining the system directly. A fusion-powered Starship could capture the first close-up images of another planetary system. It could analyze alien atmospheres and search for biosignatures. It might even discover evidence that life exists beyond Earth. Imagine witnessing the first sunrise ever recorded from a world orbiting another star, or receiving detailed images of landscapes that no human eye has ever seen before. Such discoveries would fundamentally transform our understanding of our place in the universe. If even the simplest form of microbial life were found, it would prove that life is not unique to Earth and may be common throughout the galaxy. And if no life is discovered, that answer would be equally profound, helping us understand just how rare and precious our own planet truly is. Either outcome would mark a turning point in human history, making the first mission to Alpha Centauri one of the most important scientific expeditions ever undertaken. Such an achievement would not simply expand our knowledge of space, it would redefine humanity's future among the stars. As of June 2026, it would be inaccurate to say that interstellar travel has been completely solved. Significant challenges remain. Practical fusion reactors are still under development. Superconducting technologies must become lighter and more efficient. Long-duration spacecraft systems require further advancement. Protecting crews from decades of radiation exposure remains a major engineering obstacle. Yet what has changed is the nature of the conversation. For the first time, scientists are no longer debating whether interstellar travel violates the laws of physics. Instead, they are debating how to build the technologies required to make it happen. Every major component of a future fusion-powered Starship, fusion energy, superconducting magnets, advanced materials, autonomous artificial intelligence, and radiation shielding is already being developed in laboratories around the world. The pieces are slowly coming together. For thousands of years, humanity looked at the stars as unreachable points of light scattered across the night sky. For centuries, they remained objects of curiosity and imagination. For decades, they belonged exclusively to science fiction. But now, for the first time in history, we possess a plausible engineering roadmap that could transform another star system into a destination rather than a dream. The direct fusion drive represents more than a revolutionary engine. It represents humanity's first serious attempt to become an interstellar species. The journey will not be easy, and it may take decades before the first true starship leaves our solar system. But when that day finally arrives, future generations may look back on this era as the moment humanity stopped thinking like a planetary civilization and began thinking like a galactic one. So here's a question for you. If a fusion-powered starship were preparing to leave for Alpha Centauri tomorrow, and the journey would take 40 years, would you volunteer to go? Let us know your answer in the comments below. If you enjoyed this video, don't forget to subscribe, like, and turn on notifications for more explorations into future technology, space travel, artificial intelligence, and humanity's future among the stars. The universe is waiting, and for the first time we may finally have a way to reach it.